Open. Nice to see everyone here. I'm Oliver. I'm a postdoc in Neil's lab at UCL. I've been here since just before the pandemic. And I'm going to tell you about some stuff that I've been working on for the past 3 years or so. And as you might notice, I expanded the title a little bit from the invitation into consolidation of sequential dynamics during planning. And that's not just to be difficult, but in trying to highlight that in the topics we're going to talk about today, there is a couple of interconnected but nested questions that we're going to try to tackle one after the other. All of which I think are very important, that I'm very interested in. So the first one is really about how does planning work? And you know, you might think of it as a toy example, like, you know, when I cycle home from here at the end of the day to where I live, close to Archway, how do I plan my route as I go home? And from the perspective of reinforcement learning, there's sort of a canonical answer. The answer is through model-based reinforcement learning. And what that means is really that in my mind, I have a world model of the way in which various states in the world relates to each other. And as I plan, what I do is I actually go step by step through that model and sort of roll out that plan through this transition model. And that, as we'll see, confers me with a high level of flexibility in my choices. So this is a type of representation that's based on these one-step transition. But the past couple of years, there's been other suggestions that there are other types of representations and algorithms that can also confer a level of flexibility or the ability to plan decision-making. A very prominent one of those is what's called a successive representation. And that's really just a type of representation that essentially holds the things that you usually experience when you take a particular action, essentially. So you don't really represent the relationship between these things. You're simply saying, when I make this choice, these are the states in which I'll end up. So as opposed to the model-based solution, where it's like I roll a plan, which is, you know, I'm going to go to King's Cross, then I'm going to go out through Kentish Town, then I'm going to go to Tufnell Park, Archway, etc. The successor representation would be like, if I take this route, I'm going to encounter Kentish Town, Archway, King's Cross, Tufnell Park, etc. I'm simplifying quite a bit here, but this is a toy way of thinking about it. Now, both of these algorithms confer particular types of flexibility. So for instance, if I get a new piece of information that some part on this route is now more valuable, say that there is some handout, or for instance, the Kentish Town Lidl just closed down. So suddenly, actually, the value of taking this route has decreased to me, you know? And if someone tells me just before I'm about to head home that, oh, actually the Lidl closed down, then I can use either of these two representations to actually downgrade the value of that route, you know, because Kentish Town is in the model-based representation and in the SR representation. So both, and this is what's called reward evaluation or something. You get new information about which states in the world are rewarded, and you can adaptively adjust your actions. But there are other types of information you can get. For instance, let's say someone before I cycle told me that now there's been an accident somewhere between King's Cross and Kentish Town. So that's very useful for me if I am a model-based planner, because I actually have that whole map in my head. I know that I'm going to have to pass through from King's Cross to Kentish Town. That means that that path is no longer available. But if I'm an SR learner, I don't actually have that sequential information. And so there's no way for me to integrate that information into the representation that I have of the states that are likely to follow as I take a particular path. And what that means, as theory and empirical work has shown previously, is that only the model-based out of these two algorithms is capable of doing transition revaluation. So both can do reward, but only one can do transition revaluation. The thing is, however, that there are very few papers so far that's demonstrated this distinction, and the ones that do are still not particularly high-powered. Also, even for the ones that have demonstrated model-based learning, we're not entirely sure that this behavior that's capable of both reward and transition valuation actually relies on these sorts of rollouts, like sequential rollouts, as hypothesized up here. All right, so that's the first question. The second question is sequential dynamics in the brain related to model-based planning? And there's been a lot of interest in sequential dynamics in the brain in the past 10, 20 years, maybe the most notable being something like replay. So essentially, this would be a canonical example from Firefly and Fox, but the animal sits still, and yet in its brain, you have these sequences of play cells that are playing out that are representing essentially sequences through the space. Fascinating phenomena. And, you know, a lot of people really think that this sort of phenomena, these sort of sequential rollouts, are related to this sort of rollout that we think about in model-based planning. And yet there's actually surprisingly little evidence that that is the case. And certainly a huge, like a substantial amount of negative result, both in humans and rodents. So it's complicated. So the third question is, what's the role of consolidation? What's the role of consolidation of the transition model in planning and sequential dynamics? And so the idea is essentially, the idea is that model-based rollouts happen through some transition model, and that model of the world has to be somewhere. And people have thought for a long time that, well, there's the hippocampal place map, there's cognitive maps, maybe it's seated in the hippocampus. And that was the hypothesis that I pursued for my PhD, where I worked with patients that had lesions due to epilepsy to either the left or the right hippocampus, and showed that specifically the size of damage to the right hippocampus correlates with these patients' ability to do planning, essentially. If they have more damage to the right hippocampus, they are biased towards a more model-free or more habitual strategy, essentially. So that was what I did. And then a year later, 3 years ago, a really interesting paper came out from the Belaine lab by Bradfield et al., which essentially showed in rodents that, yes, it does seem like the hippocampus is important for reward evaluation, but it seems like the role might be transient. So it's very important on day one when they just did the training, but then you put the rats in 7 days later, and then you can ablate the hippocampus and they can still do the reward evaluation. So the hippocampus is only necessary early on, but not later, after it's consolidated. And the reason for that might be answered by standard consolidation theory, which essentially states that initially memories are encoded in the hippocampus, and then over time, the hippocampus talks to cortical areas to transfer out information into the cortex so that a particular piece of information becomes independent of the hippocampus. And recent years have seen particular interest in these sorts of models with regards to the communication between the hippocampus and medial temporal lobe and the prefrontal cortex. And the idea here is that the prefrontal cortex specifically is meant to be able to extract from the hippocampus a sort of gist-like representation, a schema-like representation, sort of like a generative model of the world as Eleanor presented on here in lab meeting a couple of months ago. And so these are all very interesting ideas, but there is still not very much evidence to support many of these notions. So in order to test this, and I will say that this project really exists as a result of this, in response to this study by Bradfield and colleagues, we created a new task for humans, a behavioral task to then put in the MEG scan. And it's got some unique features with regards to reinforcement learning tasks that I'm going to tell you about now. So first of all, this task is split into two phases. There's what we call a training phase, and there is a revaluation phase. So on day one, they do a training phase, and then straight after they do the revaluation phase. And then later, we bring them back 7 days later, put them in the med scanner, and give them the revaluation phase again. Okay, so how does this task work? So in this task, they have to essentially learn to navigate this circle, this circuit of objects. So there are 9 objects arranged in a circle, 3 which are animals, 3 which are vehicles, and 3 which are fruits, 3 which are yellow, 3 which are green, 3 which are red. So there are 2 dimensions with 3 features each. So I'm going to first tell you what a training trial looks like. So a canonical training trial might look something like this, you know. So it'll tell you with text like this, for this trial, you're going to start on the taxi. You're going to stop on whatever next thing is red, and you will be rewarded by anything that is an animal on that path, and you'll get 2 points. And anything that is not of that category will subtract 1 point. So you'll get from that category and subtract from everything else. And then you have to make an accept or reject choice based on this information. Let me get back to what that accept reject means. But whether you choose accept or reject, you're now going to see a sequence playing out. And that's essentially going to be, assuming that you stay on the taxi, you're next going to move to the frog, and you're next going to move to the bus, and then the trial's going to end. That's the trial. And when you hit the frog, because animals are currently rewarded, you're going to get 2 points, and when you get the bus, you're going to get -1 point. So that means that if you pay attention to this trial, you'll know that the total points for this trial is 1 point. And the task, what you're tasked with here, accept or reject, is essentially to accept when it's positive and reject when it's negative, you know? That's it. And if you say reject, you always get 0 points, essentially. So it's the, you know, it's the default option. So it's like, accept. Do you accept this offer? Do you want to take the risk? Do you want to take the rewards? Or do you want to take the losses, essentially? And what's unique about this training phase is that for a given start state, say taxi, it's always paired with the same color and the same reward category. So what that means that whenever you start in taxi, you have always the same contingency, and you see exactly the same things playing out every time. Which means that you should always, every time you see taxi in this case, you should always accept, you know, because it's always going to give you 1 point. And that's, you're going to see that thing whether you accept or reject again and again and again. All right. So what happens is that they do this training phase, and for each of these start states in a pseudo-random order, you start in each place 20 times, essentially. And over these 20 times you start in, say, the taxi, participants reach at least 85% accuracy on those choices. But to say that they're accurate here, whether they get the right answer or not, doesn't tell you anything about what strategy they're using. For that, we need the revaluation phase. So in the revaluation phase, one of the huge differences is that there's no feedback whatsoever. There's no images or no point-blank feedback. It's just going to be choice after choice after choice. After they've done with training, they're never going to see any images or any points ever again. No more feedback. And now, in the revaluation phase, every start state is now going to be presented with every combination of stop color and every combination of reward category. So that means that you actually have 9 times 3 times 3, 81 unique planning problems, 81 unique probes, of which they've only experienced 9 before in the training. So because 1 per start state, essentially. So you get 72 unique problems. And the idea here is that changing the rewards lets you see whether they're able to do reward evaluation. And changing the stop, the stop color essentially sees whether they're capable of doing transition evaluation, whether they assume that they're going to see the same states that they always did when they start in a particular place, or if they can, you know, infer that they're supposed to stop in an early place or actually extend beyond that into what they've learned from other sequences. And so what that means is that the different strategies have different, the MB and the SR strategy have different predictions in the reward evaluation phase. So if you think about this case forever, given that this is what they experience during training, if we have a model-based learner, then they know that after the taxi comes the frog. So that means that they should stop after the frog. They're not going to get any longer in that task. And vehicles is currently rewarded. So that means that after frog, let's stop, and that's a -1. So the total points is going to be -1. That's what they expect if they're a model-based planner. If, however, they are an SR planner, They can't do this reward evaluation. So essentially, they're just assuming that they're going to see whatever state they've always seen in relation to this start state. But they are capable of doing the reward evaluation. So now, rather than thinking they're going to get 2 points for the frog and -1 point for the bus, they now think the opposite, which means total 1 point. And so this would be an example, essentially, where a model-based planner and SR planner make opposite predictions about whether you should accept or reject. So what I can then do is that for each trial, I make a prediction based on these two strategies about whether they should accept or reject, and then I regress choice on that. And so I'm going to show you data from that, which is simply a logistic regression. That is, whether the prediction from these two strategies can predict to the extent that that predicts choice. And as I say, I have done model fitting too, looking at a whole bunch of different models, and this is the best fitting model. But I'm not going to tell you any more about that fitting procedure. You can ask me later if you want. And all I'm going to show you today is data from the revaluation phases. That's it. And this is all done inside the MEG scanner. And I should say, during the evaluation phase, they do on each day, they do 3 times each of these 81 problems. So there's essentially 273 trials on each day, all of them without feedback. Furthermore, when they come back on day 7, they don't get any reminder of the sequence, nothing at all. You know, it's like they just left, essentially. Okay. So what we find, first of all, is that when we look at everyone, we find that there's a super strong component both of model-based planning and of SR planning. That is to say, there's a sort of hybrid, this hybrid stuff at play, where essentially they're both employing strategies that are capable of both transition reward evaluation and strategies that are capable of only reward revaluation. And as you can see, there's a lot more variance across participants on the MB estimate. And the reason for that is because there is enormous amount of individual variability on the model-based estimates across participants. It's really hard for me to overstate how strong it is. What it goes from is within participant, 0 model-based effect, that is, they are not model-based at all, to within participant, so model-based that the p-value cannot be captured by MATLAB because it's too small, as in almost perfectly model-based. So there's an enormous variation within this task, and it's a very powerful task that captures a lot of that variance. So what I'm going to do to move forward, I'm not saying this is really a result, it's more of a presentation device, is I'm going to split this data into 2 groups. I'm just going to median split them based on how model-based they are. I'm not saying that there are 2 groups, I'm just saying this is going to be a very convenient way to show you what's going on here. So essentially what we have is the half of the population that's super strongly model-based and has a bit of SR in them as well. So essentially they are primarily using the model-based strategy. And we have another group which have no model-based, as a group, have no model-based estimate at all and is only using the SR. So I'm going to call these the MB group and the SR group for convenience. And I should say any error bars that will be in this presentation is a standard error. Yes. Yeah, if it's clarifying, yes. I mean, you can ask it, but it's roughly, yeah. So I'm not making strong claims about that. I mean, you could also call it the MB and the no MB group, essentially. We have one group that has a very strong element of doing some sort of sequential, at least being capable of doing transition evaluation, and another part of the group that can't, you know. But the question is, this group that can do transition evaluation, are they actually doing this sort of rollout? And how would we know that? Well, one thing we can do is to think about reaction times, because the idea is if I have to plan further or if I have to plan with more stops, you know, the plan should, if you're rolling out, take longer, you know, because you have to integrate further, essentially. And in this task, they either have to plan 1, 2, or 3 steps far, you know. So what we can do in these 2 groups is to look at how reaction time is modulated by how far they actually have to plan after we've changed we've told them the new planning depth. And what we see is something very, very strong, which is that in the model-based group, there's a super strong modulation of reaction time by planning depth, which is not seen in the SR. And if you flip it so you look at the old planning depth during training and how that relates to the SR, those are not significantly related in the same sort of way. And I should also say that across participants, the extent to which a participant is model-based and how steep that slope is, that is how much their reaction time is modulated by planning depth, those two quantities have about a 0.9 correlation, which is, I'd say, about as strong as you get in behavioral science. So strong that I would go on to say that these are essentially the same parameter, and I've replicated this in online samples as well. So it is just true that to the extent that people can do transition revaluation, their reaction time are also modulated by planning depth. Yes?
Do you have evidence that a single individual starts the task at the moment stage will swap from one strategy to another?
I'll slightly come back to that. So I'm not going to talk at all about the learning phase now, but there will be some changes in the strategies that they rely on from day 1 to day 7. That's true. But you should remember there's no feedback, so it's not learning, Yeah, I mean, something's going to happen, but what it is will. So we're going to now look at some MEG data, and what we're going to use is what we call a dynamic similarity analysis, which is just building on what a lot of stuff before. It's essentially like an RSA, where we look at the representational similarity between different trials along the, but now we're going to do it along the entire neural dynamics that plays out during a trial. But let's start simple, and let's just talk about representational similarity. So I'm just going to tell you how to go about this sort of analysis. So what I first do is I take the MEG data and I transform it into voxel space using the beamformer forward model, essentially. So now each participant has about 2,000 voxels. Next, I split the data in two halves. And I'm going to repeat this procedure many times with random splits, etc. And then I z-score within each half. And that means I'm going to take out any variation that's general to all trials. I'm just going to be able to look here at differences between various trials. Next, I'm going to take all the trials where they start in state n. Let's say, for instance, where they start in the state taxi. And I'm going to average all those trials. I'm going to do that in one half, and I'm going to do that in the other half, essentially. And then for that average, for every time point of each half, on the x-axis, what I'm going to do is essentially do the representational similarity of one half with the other half for essentially the first 3 seconds of each trial. Does that make sense? So what that means is that like what this point here is representing essentially is in the first half, 2 seconds in, the z-scored voxels correlated by, in the second half, 1 second in, the z-scored voxels there, essentially. Just a simple Pearson correlation. That's it. And so it's really interesting what we see here. So we see a very strong diagonal through the first 3 seconds, And what that means that there's a diagonal means that there's dynamics going on. It means that a particular start state is not just related with a particular patterns of activity, but rather it's like a series of patterns, that there's a particular pattern that appears at 1 second, and there's another one at 2 seconds, there's another one at 3 seconds, That's why it's diagonal, because what happens at 1 second doesn't correlate with what happens at 3 seconds. Only 1 with 1, 3 with 1, etc. And because I've z-scored, this is not representing anything task general. So for instance, if I correlate instead n, starting in n, with not starting in n, like any other one of the states, there is nothing, So this diagonal here is unique to each particular start state. And so what I'm going to do next is I'm going to plot here to you the mean for the whole for the whole group, essentially along this diagonal here. And what you can see is that it stays way above the 0 line for the entire 3 seconds. That is to say, the state is decodable, is reproducible for at least 3 seconds of planning time. And it peaks around 400 milliseconds, which is way later than what you get from a usual visual decoder. And I should also say that because the start and the reward category changes, they don't always see the same things on screen either, you know. And also, I mean, if you just do a visual decoder or something like that, that one will usually peak at 200, and then it'll go down at about 700 milliseconds, something like that. But this one stays above 0 for the whole of 3 seconds. So what's going on with that? What is it that's being reproducibly activated over trials, essentially? Another very interesting thing is if we split this graph by model-based and SR participants into the 2 groups, suddenly we see that it's primarily driven by the MB group. That there's a lot more reproducible dynamics in the MB rather than the SR. Overall, significantly, and at many time points. All right. So what is this about? What is this diagonal about? You know. So one interpretation of this could be that the peak there in the beginning, that is actually decoding the concept of the start state, you know. But then the reason why you're seeing a diagonal is because then comes the things that come after. Then, you know, so if it's taxi, then it'd be frog, bus, banana, etc. That's actually what we're decoding here. So how would you test for this? Whether that's actually the sequential activity we're seeing? Well, you could compare it to trials that start in n-1. Because the idea would be that if you start in n, you know, on average, you're gonna go to n1, n plus 1, n plus 2, n plus 3, etc. And if you start in n-1, you're going to see the same sequence of stuff. It's just that you're not going to see that sequence until you've passed through n-1. So it's the same sequence of states that you're going to see. It's just that in the case of n-1, those states are going to come on with a lag, a temporal lag, that's essentially the time it takes to go from one state to the next in your mind as you're planning. So the lag is the time it takes for you to plan from one state to the next in this task. And what that's going to look like if you plot it, if you plot start state n versus on the y-axis start state n-1, what that's going to look like, because it's the same dynamics, it's just shifted with a lag, the way that's going to look like is a diagonal that's been shifted upwards, essentially. And what's fascinating is that if you look in the model-based group for this metric, that is in fact what you see. A very strong upward shifted diagonal, roughly between 0 and 1 second. And if you look in the SR group, there's no such thing. And what this means is that there's actually very strong evidence that there is a sequential dynamic playing out in the model-based group. They're planning and they're going from state to state with about a rate of half a second, 700 milliseconds per state, something like that. And what I'm going to do now to just illustrate that point is I'm going to take the average along these lines, essentially. This is what I call dynamic similarity. That is, I'm going to do the average along the dynamics along the entire dynamics for a particular lag. So that means that this value here for the SR group, that's the average along the main line. And average along this line here is going to come out here. And what you see is that in the range roughly 0 to 1, see, it looks like it bleeds over, but that's actually due to smoothing. In the range 0 to 1, in the model-based group, there's a lot more of this forward sequential dynamics. And you can also do this analysis, not just doing the n versus the n-1, but you can do it with the n-2, the n-3, n-4. And what's amazing is that, you know, here we see we're doing this essentially averaging here in the same way as we did before. But what we're seeing here is that if we compare the n to n, we see a very strong central diagonal. And then comparing it to n-2, that's the next one. n-2 is the next one, n-3 is the next one, and n-4 is the next one. So we can see so strongly in the data how the further away two states from each other are, the less similarly they are represented in this task. And that's only true for the model-based group, not at all for the SR group. Another kind of cool thing here is that you know, if it is in fact the case that they are, you know, rolling out, that we're capturing here like a plan, a thought as it's happening, you might think that if they're thinking faster, they might plan faster. So what I did next is that for each participant, I split median split the trials where they had the fastest reaction time and the slower reaction time. And then taking the n versus the n, I plotted them against each other. So on the x-axis, it's the fast reaction time, and on the y-axis, slow reaction times. And what you see is essentially a diagonal that's now shifted upwards, which means that the same dynamics that take 3 seconds when they're slow to react takes about 1.5 seconds when they are fast to react. So we can actually not only decode the content of these plans as they're evolving, but actually the speed of the thought, which to me is absolutely amazing. And indeed, if you look in the SR group that don't have any of these behavioral signatures, we don't see any of this stuff. So we can talk later about what this method offers, but this in summary is just, we're seeing this sequential rollouts and sequential neural dynamics in these model-based participants. In the SR, we do see a diagonal that's above 0 when we compare the n minus n, but we don't really think, it doesn't look like there's any sequential information inside their planning, and we don't really know what's going on with the SR. But I think for the MB, it's very, very clear, both behaviorally and neurally. So I know we're running out of time, so I'm going to go straight on to consolidation, because I told you we're doing this in 2 different phases. Day 1 or in 2 different days, day 1 and day 2. I just want to remind you again, there is no feedback in any of these phases, and there's no reminder when they come back. So any effect is just going to be from their active or passive processing of these stimuli. There's no new learning. So you might wonder, how does the behavior change when they come back a week later? What do you think, Hani?
They become more model-based.
That is right. The model-based people become more model-based. And that's the only change that really happens, So the model-based group becomes significantly more model-based when they come back a week later. And what's amazing, if you look at these metrics that I have of sequential dynamics, so first looking at the n versus the n in the model-based group, you see that it just cleans up so nicely by the time they come back. And in fact, if I do the average along that line, essentially, you see that it's way above the day 1 representational similarity throughout the 3 seconds. And indeed, if I do the n versus the n minus 1 in the model-based group for the day 1 and day 7, what you see is that what is a little patchy on day 1 cleans up into almost a perfect diagonal that's been shifted up by, on average, about 500 milliseconds or 700 milliseconds by the time you get to day 7. And here you can see it average across those lines, essentially, for day 7 and day 1. And this is not at all true for the SR group. If anything, they get worse and more disordered in their neural dynamics. So the last thing I'm going to talk about is source localization, which, so far, every one of these points on this graph is essentially a correlation, and so essentially the way I got that correlation is just by you take all these z-scored and you just do you do cross multiplication like this, like a pairwise multiplication, then you just average those values, and that's the correlation. That is approximately the correlation. But you don't have to average it. You can just take them, each one of these voxels on their own, and just see which of these voxels are actually driving that correlation. So it's a bit like doing an RSA, but you're doing it 1 voxel at a time, and I place them on their respective places on the brain. And so the contrast I'm going to show you now is across the brain. When I do the contrast, essentially, of what I'm going to look at is from like 0 to 1, where in the brain is this measure, this dynamic similarity that reflects sequential dynamics, the n versus the n minus 1, that's bigger here for the MB than from the 0 to 1. What's explaining this difference? Where is this difference between the 2 groups coming from? And when I do that, there's only one area when I do a whole brain family-wise correction that survives, and that is the right hippocampus and right entorhinal cortex, which incidentally is the area which in the lesion study that I worked on before, I showed that damages to this place impacts patients' ability to do model-based planning. And next, what I did was I did the same analysis, but rather than taking all the data, like I did here, to look for where the sequential dynamics is playing out, where essentially they're playing out. This is what this is telling us. Where are they playing out through a world model, essentially? And it happens that it's in the hippocampus. And what I did next was that rather than taking just the raw data, I contrasted day 7 to day 1, comparing the MB and the SR group. And the only area that survives whole volume correction is an area in the prefrontal cortex that is somewhere between the lateral frontal cortex, OFC, sort of the IFG, so Burgess area. I don't want to say too much exactly what it is. It also expands quite a lot if you lower the threshold a little bit. And there is the only other area that's close to significant is the exact same area on the other side of the brain. So there's definitely something going on in this band in the frontal cortex. And I guess what this is really indicating is that overall there is this sequential dynamics in the hippocampus in this task, which is then over the course of this task, essentially moving into the prefrontal cortex exactly as is predicted by standard consolidation theory. And just to summarize then, model-based planning, which is a bit, can do a reward and translation evaluation, seem to defend the behaviorally on sequential rollouts. And they in turn seem to be completely related to sequential dynamics in the brain. And this model-based planning and the corresponding sequential dynamics is indeed strengthened over the course of consolidation, and that this sequential dynamics in the model-based relative to the SR group can be seen in the right anterior hippocampus and increasingly in the PFC following consolidation. And so I think in showing these things, what we've really done is sort of elucidate the hitherto unexplored, but what it turns out to be maybe absolutely critical role of these memory processes in the evolution of adaptive behavior. And that's it for now. And I want to thank collaborators, Evan Russek, who helped me design this task, and my supervisor, Neil Burgess, has been incredible. And also thank to this whole building, because this is where it was collected. And in particular, Daniel Bates and Yasmin, who had to deal with my neurosis, and George as well, who's been very, very helpful in the analysis as they progressed. And also thank you, Dan Bush. That's it. Thank you.